Alright, the problem comes from Chapter 2, One-Dimensional Motion, from Edition 8. An attacker at the base of a castle wall, 3.65 meters high, throws a rock straight up with a speed 7.4 meters per second from a height of 1.55 meter above the ground. A. Will the rock reach the top of the wall? B. If so, what is the speed at the top? If not, what initial speed must it have to reach the top? C. Find the change of the speed of a rock thrown straight down from the top of the wall at an initial speed of 7.4 meters per second and moving between the same 2 points. D. Does the change in speed of the downward moving rock agree with the magnitude of the speed change of the rock moving upward between the same elevations? C. Explain physically why it does or does not agree. Let's start off with just a drawing, and a drawing just helps you make sure you got all your relevant variables. So we've got the top of the wall, and then we have the base, we have the object being thrown up, and we know that the initial velocity I is equal to 7.4 meters per second. We also know that its height is 1.55 meters. Height of the wall, 3.65 meters. And we know it follows some path. We'll draw that path and then comes back down. Now the question is, here, this will label as VF. We know that that is equal to 0, and we'll call that YF. At this point, we'll call this the position Y at the top, and we have a velocity at the top. Both variables are unknown. We also know that it takes some time to move between this point and the initial point, so there's some time variable involved. And the first question we want to ask is there a relationship that we know of that involves the time, the acceleration of gravity, and the initial velocity, where we can predict the height the particle will reach? And if you remember, we know that there is a relationship that the final position YF is equal to the initial position YI plus whatever initial velocity in the Y direction times the time minus 1/2 g times the time squared. Now, what we don't know is the time. We know VIY, we know G, we know YI. If we had the time, we could, in fact, determine whether or not YF was high enough to be higher than the top of the wall. Is there a way to find that time, or is there a relationship between what the variables that we do know, gravity and time? Well, we know that the final velocity at the top is 0, we know the initial velocity, and we know that there's a relationship between the final initial velocity, gravity, and time. And that is that VF is equal to the initial velocity minus GT. Now, since all three quantities are known except time, we can solve for time and obtain that time is equal to VI over G. Of course, we know VF is 0. And that time calculates out to be equal to 0.755 seconds. Now we can go ahead and take this time and we can put it back in to this equation here. And so we have YF equal to, and YI initial was 1.55 plus 7.40 meters per second times 0.755 minus 1/2 times 9.8 meters per second squared times 0.755 seconds squared. And that comes out to be equal to 4.34 meters, which is greater than the 3.65 meters, which is the height of the wall. The next question is, what is the speed at the top of the wall? Or what is Vt? Well, we know Vi, we know G, and we know Y final, and we know Y initial. So can I use these variables and calculate time? Well, recall that there's the relationship Yt, this will be the final position at the top of the castle, will be equal to Yi plus Vit minus 1/2 Gt squared. Now, Yt is 3.65 equal 1.55 plus 7.4 meters per second, and all this is times time in seconds, minus 1/2 times 9.8 times time squared. We can set this up as a quadratic equation in time, and we will have 0 equal minus 2.1 plus 7.4 meters per second times time minus 1/2 times 9.8 time squared. Setting up as a normal equation, getting ready our normal quadratic equation, we would have 1/2 times 9.8 t squared minus 7.4 t plus 2.1 equal 0. And if you remember the quadratic formula, minus b over 2a plus or minus the square root of b squared minus 4ac over 2a. And that'll result in a time equal to 0.567 or 0.943. And of course, 0.567 is the time required to reach the height of the castle wall. Now the question becomes, do we have enough, given the time, to calculate what the speed is at the top of the wall? Well, once again, we can go to our relationship that the final velocity, which would be v at the top of the wall, is equal to the initial velocity minus g times the time. And that's simply going to be equal to 7.4 meters per second minus 9.8 times 0.567 seconds. And that turns out to be equal to 1.8 meters per second. The next question was, what about a rock thrown downward? In this case, of course, we're going to have our castle wall, and then the object is being thrown down at a minus 7.4 meters per second at an initial height of 3.65, and then we want to calculate its change in velocity when it crosses this position, 1.55 meters. And what is the velocity final? Well, now I ask, is there a relationship or an equation that contains my initial velocity, my final velocity, the distance I travel, and the acceleration due to gravity. And if you recall, there's an equation, vf squared equal vi squared plus 2a delta y. And vf squared will therefore be equal to, well, it's 7.4 meters per second plus 2 times a minus 9.8 times delta y, which would be 1.55 minus 3.65. On calculating that, you obtain EF squared equal to 95.92, which means that VF equal to 9.8 meters per second. In our first case, where we're dealing with the object being thrown up, our final velocity was equal to 1.8 meters per second. Our initial velocity was equal to 7.4 meters per second. So the magnitude of the change in velocity will be equal to 5.6 meters per second. In the second case, we had VF equal to 9.8 meters per second, the initial equal to 7.4 meters per second. Both these in the negative direction, but we're only interested in magnitude. So my change in velocity will be equal to 2.4 meters per second. So the change in velocity in the second case, where the object is thrown down, is less than the change in the first case where the object is thrown up. And we can physically understand this by the fact that in the first case, our average velocity, will be greater, or will be less than the average velocity over here, simply because our V final here will be less than our V final here, and they both have the same magnitude of their initial velocity. We can also observe that since the average velocity here in the first case is less than the average velocity in the second case, then the time going up is going to be greater than the time going down. And since our change in velocity is equal to minus gt up, and here to be minus gt down. Since t up is bigger than t down, then the change here will be bigger in the first case than it is in the second case. End of problem.